Hello and welcome to another installment. This is another instructional video for this course, and today we're going to be continuing our discussion about electrons. If you remember last video, we talked a little bit about electrons and what was discovered about the behavior and the structure of electrons in an atom because of scientists' understanding of light and how light behaved. So, if you remember, we talked a little bit about electrons and them residing in specific energy levels, certain regions, positions for the atom and for different elements. So we're going to continue that topic. We're going to continue to talk a little bit about the electron, and we're going to talk how electrons are configured or arranged in the atom. So what is the electron structure in an atom? All we've established up to this point is that electrons are going to reside at different energy levels, specific energy levels. Well, let's get a little more specific about those energy levels. All right, the electron structure of an atom is very important. They use the electron structure to predict bonding in molecules, the charge an atom might have, or the physical properties of elements. In order for scientists to describe the electron structure in an atom, they give electrons addresses. Just like your address might include your house number, your street, your city, state, an electron's address has multiple parts. In this activity, you're going to learn how the electrons fill up the available spaces in an atom and how their addresses or configurations, configurations is just their arrangement, are assigned. So we're going to look at this model here. It's kind of an illustration, an analogy, if you will, to the addresses of the electrons. So imagine that you have a boarding house, meaning where you allow people to stay and sleep. And in your boarding house, you've got sunny rooms over here on the left side of the home, and you've got pink rooms over here on the right side. You've got a kitchen down below. And then you have a time, and at that particular time there is a certain number of people in your boarding house. And since you're the manager, you're going to track some type of code. You're going to track some type of code here in order to kind of represent who is in your house, and actually where are they in your house. Okay? So each time you are going to use your code in order to describe where people are sleeping in the boarding house. So let's answer some of the questions here. We're going to start really simple, really basic. Examine the boarding house diagrams in Model 1. Match each symbol below with its most likely meaning. So this right here is going to mean a boarder. That's a person right there. That is a person or a boarder in your boarding house. This diagram right there is a bunk bed. So this, by the way, I can put these in here. That's one. That's three. That's one. So this is your bunk bed. And then this here is the code. That is the code for describing the number of boarders and where they are staying. How many boarders were in the boarding house at 5 p.m.? At 5 p.m., we look back up at our model. At 5 p.m., how many boarders, how many people are in the house? 1, 2, 3, 4, 5, 6, 7, 8. So there are 8. Describe how you determined your answer to part A. You're just going to count the dots. Okay? Question number 3. Question number 3, examine each diagram in Model 1 and the corresponding code that the manager is using. Using the following manager's code. Here is an example of the manager's code. Underline the floor numbers. So let's look a little more closely at the code and how it relates to the arrangement of beds. So this person, you just have one person on the first floor in a sunny room. Here you've got 2 people on the first floor in the sunny room. You've got 2 people in the second floor of the sunny room, and you've got 2 people in the pink rooms on the second floor there. So it looks like, because you'll notice down here now, once you start filling the third floor, then we add to that code. So it looks like the big number here is telling us the floor number, the floor level. Okay, the floor number is going to be the big number. Circle the types of room. So we have sunny, or pink. Draw a box around the number of borders. Well, this just means you have 2 borders, that small 2, that small superscript 2 there, means you got 2 borders in a sunny room on the first floor. Here, 2 borders in a sunny room on the second floor. Here, 4 borders in a pink room on the second floor. The manager of the boarding house has some very strict rules on how beds will be rented out for the night. Examine the diagrams in Model 1 and the statements below to determine the phrase that best describes the manager's set of rules. Circle the correct answer. So, let's look at 4A. The boarding house will rent out beds on the which floor first? Well, as this house got fuller and fuller, as more and more people came, you'll notice that he filled the lower levels first. So floor 1 got full, then floor 2 got full. He's not going to put anybody in the third floor until the first 2 are full. Okay? So you're going to fill the first floor first. Then boarders are only allowed to double up in a bunk bed in a room when, well, let's look at the model. Notice he did not allow people to double up until there was at least one person in each of the bunk beds. Alright, that makes sense. People like to spread out, have their own bed. Electrons like to spread out because they repel each other. So you're not going to start to double up in a bunk bed like right here until you've got one electron, or one person in this case, in each of the bunk beds. So the answer here is all bunk beds are occupied. Okay? The next floor of rooms will be open for boarders only when the next floor, that is, will be open for boarders only when all of the bunks on the floor below are occupied. So everything has to be occupied in the floor below before you move up to an upper floor. The pink room will be open for boarders only when all of the bunks in the sunny room are occupied. You're going to fill the sunny room first and then move over to the pink room. So, provide the manager's code and a boarding house diagram below showing 12 boarders present. So, if we have 12, let's look at our model here, by the way. 2, 4, 6, 8, 10, 12. So, if you had 12, this is 2, 4, 6, 8, 10, 12. There's 13. So if you had 12, you would just be showing this right here. Okay, I'm not going to draw it all out, but the code would be everything except for this last part. So your code for 12 would just be this right here. You would have, on the first floor, you would fill the sunny room first with 2 people. Then you would move up to the second floor, and you would fill the sunny room with 2 people. Then you would start to fill the pink rooms, still on the second floor, pink rooms, and it looks like the maximum in the pink rooms, because there's 3 bunk beds there, 2 in each bunk bed, would be 6. So that's 2, 4, 10. Now you can go up to the third floor, and you would fill the sunny room with 2 more, and now you've got your 10 there. So you got your 12 in order to have this arrangement, and that would be the code that you would have. Okay? All right, let's look at model number 2 now. You'll notice very similar in the diagram. Now we're going to be talking about, instead of a boarding house, we're going to be talking about actual energy levels for electrons. So these are ground state orbital diagrams and electron configurations. Ground state means every electron is at its lowest energy position. None of them are excited and jumping up to higher energy levels. Okay? So, and the arrows are representing electrons. You're going to have an arrow that is pointed upward and an arrow that is pointed downward, and that's because it's believed that electrons, if they are in the same orbital, are spinning in opposite directions. So here's hydrogen. Hydrogen just has one electron. One electron, you're going to fill that 1s orbital. This is like the first floor sunny room. This is the area where an electron is first going to be positioned. This is the lowest energy level available for an electron. So you're going to fill that first. So this is representing, this upward pointing arrow is going to represent the one electron for hydrogen in its 1s orbital. Now instead of sunny, this S actually stands for spherical, because that is kind of the shape of an s orbital. Okay? When you go on to carbon, carbon has 2, 4, 5, 6 electrons, and they will fill the 1s first, 2 max, 2 electrons per orbital. That's the maximum, no more. So 1 up, 1 down, 1 spinning one way, 1 spinning the other way. 2 electrons in the 1s orbital. Then you can move up to the higher energy level, the second energy level. And you first, because the 2s gets filled first, it's at just a slightly lower energy level. You would have 2 in there, and then you begin to fill these p orbitals, the pink rooms. Well, the p orbital. They're p because they have a slightly different shape than the s, which is spherical. And remember, you spread them out across the p orbitals because all these p orbitals are at the same energy level. So you're going to start to fill them with 1 each and then go back up and double as you see here. You don't start to double up until you have everything at the same energy level, having at least 1 electron in each of those same energy level orbitals. Okay, so you kind of get the idea here. Let's answer some of the questions. Examine the orbital diagram and electron configurations. Match each symbol below with its meaning. So this right here is going to be your atomic orbital. That box is representing your atomic orbital. The up arrow is representing a single electron, and the up and down is representing a pair of electrons with opposite spins. 3 boxes, or however many boxes, could be 5 or 7. You might see that later on. These boxes here are all representing orbitals that are all at the same energy level. So we're going to call those, that's a sublevel. A set of orbitals have an equivalent energy. So that is number 4. And then electron configuration is like the manager's code. So this is your electron configuration, or the code that tells us exactly where the electrons are. Consider the orbital diagram for oxygen in Model 2. So, here we go. How many electrons are present in the orbital diagram? In Model 2, we're looking at the orbital diagram for oxygen. First, we're asked how many electrons are present. That's it. We're just going to count the number of arrows. How many electrons are present? So let's go back up to oxygen. Here we go. 2, 4, 6, 7, 8. So there are 8 electrons for oxygen. Based on its position in the periodic table, explain how you know that your answer to part A is the correct number of electrons for oxygen. Well, if you look on the periodic table, oxygen is located in the position where if you count across, excluding the transition elements, the main group of elements, it is in a position that tells you that it has 8 electrons. All you got to do is count. It also has an atomic number of 8. So if you count from hydrogen to helium and then keep going, you're going to come across oxygen. That's not right under helium, okay? That's kind of deceiving. You're going to come across oxygen as the 8th element. It has an atomic number of 8. That's because it has 8 protons, but therefore if it's going to be a neutral atom, it also has to have 8 electrons. Okay? Alright, question number 8. Question number 8 basically says, examine the orbital diagrams in electron configuration in Model 2 using the following electron configuration. Again, this is similar to what we did with the boarding house manager's code. Underline the energy level. It's right there. It's the big number. The sub-level is basically going to be the letter. The letter's telling you the s orbitals or the p orbitals. Those are all kind of at the, that's your sub-level, the same energy level. And a box around the number of electrons, that is your superscript. Okay? Number 9. Number 9 is saying the 2s and 2p sublevels are very close in energy. And you know that because as you move up these diagrams, this is increasing energy level. Lowest energy, this is highest energy. Okay? So notice that these two here are pretty close together, but 2s is still a little bit lower. 3s and 3p are close, but 3s is still a little bit lower. 2s and 2p sublevels are very close in energy, as are the 3s and 3p. Explain how the orbital diagram for sodium confirms that the 3s sublevel is lower in energy than the 3p. So for sodium, here's sodium, the 3s is lower. It's just drawn below, slightly lower than the 3p level. That's how they're depicting that the energy is lower, just positioning it a little bit lower than the 3p. Okay? So it is positioned lower. The lowest potential energy arrangement of electrons in an atom is called the ground state. I mentioned that. So ground state electron configurations can be predicted by a strict set of rules known as the off-ball principle. Off-ball means filling up. Okay? Examine the diagrams in Model 2 and the statement below to determine the phrase which best describes each rule. Circle the correct answer. So let's just go through a set of rules to help you understand how we are going to fill these orbitals. And therefore, remember, this is always in the ground state. The electrons are the lowest energy position possible. We're going to fill these orbitals following a set of rules. Based on where a single electron is placed, the lowest potential energy electron in an atom is found in the 1s sublevel. Okay? Based on where a single electron is placed, the lowest potential energy electron in an atom is found in the 1s. 1s is the lowest possible energy position. Okay? B. Electrons will occupy a p orbital only after you first have to fill the s orbital. S gets filled first. It's lower in energy than p. So the previous s orbital must be completely full. Then you would move up to the p orbital. Electrons can begin to occupy energy levels with the next highest integer designation. That means, 1, 2, 3, that's the big number. Only after all of the orbitals on the energy level below it are occupied. So you have to fill, we talked about this, you have to fill everything on the second energy level before you move up to the third energy level. Everything on the first energy level has to be filled before you move up to the second energy level. Okay, here's another little rule. The Pauli exclusion principle describes the restriction on the placement of electrons into the same orbital. The Pauli exclusion principle can be expressed as if two electrons occupy the same orbital, they must have opposite spins. That's why we show one up and one down. And the Hund's rule describes how electrons are distributed among orbitals of the same sublevel when there's more than one way to distribute them. Hund's rule consists of two important ideas. Based on Model 2, circle the correct answer. So basically, we already talked about this, but you cannot put two borders in a bunk bed until you have one in all of the bunk beds at the same energy level, in the same set of rooms, if you will. So electrons will pair up in an orbital only when all orbitals in the same sublevel have at least one electron. So you put one electron in each of the orbitals first, and then you're going to pair them up in their bunk beds. Okay? And then you should see that here. That is clearly marked and distinguished, especially right here. Okay, you see? You're putting one in each. You're not going to double these up until you have one. Here now, you've got 1, 2, 3, one in each of the 2p's. Now you can double them up, going back to the original first 2p. You wouldn't go up to 3 yet because the 2p is not full, but you don't double up the 2p's until you've got one in each of the 2p's. When single electrons occupy different orbitals of the same sublevel, so single electrons occupying different orbitals, they all have the same spin. Okay? So this is just showing you that all the arrows are pointing upwards if you're spreading them out. And then when you double them up, then you show that arrows all point downwards. Okay? Alright. 13. For each of the symbols below from Model 2, provide the name or description of the analogous component that was used in the boarding house model. So all this is saying is that now this right here, that represented the, oh yeah, this is our orbital, but in the boarding house, this was your bunk bed, right? So there's a bunk bed. Now we're going to be calling that our orbital. This here, this was your set of pink rooms. Now we know that in our orbital diagram that this is a sublevel. Okay? All those pink rooms are at the same level. That's an illustration or an example of a sublevel. This here was a border in the house illustration. This now is our electron. That arrow is representing an electron. This was a pair of borders. Likewise, it is a pair of electrons. And this is the manager's code. Now with electrons, this is our electron configuration. Okay, configurations. What characteristic of electrons is not well represented by the boarding house model? Well, electrons we know have a charge. Okay, they are negatively charged. Also in the boarding house, you didn't show their spin. And also, I think in the boarding house, the second floor rooms were all at the same level. So it didn't show the difference between 2s and 2p, for example, or 3s and 3p. 3s and 2p are slightly different energy levels. That wasn't shown in the boarding house model. How could the boarding house model be modified to better represent the relative energies of S and P levels? Well, you could have, for example, this sunny room, and then maybe you have to show that there are some stairs that go up to the 3 pink rooms. So you'd have to show that there's a distinction in the energy level so that it better represents our true orbital energy positions. This is a key concept. Let's not miss this. Below are 3 answers generated by students in response to the prompt. Provide an orbital energy level diagram for the ground state of nitrogen atom. In each case, indicate whether the answer is right or wrong, and if it is wrong, explain the arrow. So, nitrogen, first of all, we should figure out the nitrogen, how many electrons does it have, and let's see if they all have the same number of electrons. 2, 3, 4, 5, 6, 2, 4, 5, 6, 7, 2, 4, 5, 6, 7. So it looks, first of all, like one of them has 6 and one of them has 7. but we'll talk about that as we deal with this. So let's first of all, we have to keep the rules in mind. So keep the rules of how we fill these orbitals. Remember, we're filling the lowest energy first. It clearly said ground state. If this was excited state, you could have electrons way up here in 3p, or a fourth energy level, or fifth. But we're talking about ground state, so everything is low energy first. Fill the lowest energy first. Okay? Well, that's the problem here with A. A, notice that you jumped up to the third energy level before the second one was full. And you also did it here. You started to fill a p orbital before the 2s was full. So you broke one of the rules. You are filling higher energy prematurely, okay? Too soon. Let's look at this one. You have filled the 1s, and then you filled the 2s, and then you're starting to fill the 2p, and you have 1 in each of the p orbitals, and then you would go back and fill them or double them up, but it looks like this one is indeed correct. All right? This one, you did fill the 1s, then the 2s, and you're starting to fill the 2p, but you should have placed this one over here, pointing upwards, so that you put 1 in each of the orbitals first before you start to pair them up. Okay? Don't pair until 1 in each orbital of a sublevel. Okay? Don't pair until 1 in each orbital of a sublevel. Alright, number 15 says complete the ground state orbital energy level diagrams and write the corresponding electron configurations. Alright, excellent. We get to do this ourselves now. We need to fill these in and then write the code. So let's look at this. This is great practice for us. Here for sulfur, first thing we want to do is we want to identify how many electrons sulfur has. So if you look on the periodic table, find its atomic number and determine its atomic number, which is the number of protons, and it will also be the number of electrons in a neutral atom. And then we start at the bottom, the lowest energy level. We fill the 1s first with 2 electrons. Then we fill the 2s with 2 electrons. Then we would put an electron in each of the 2p, and then we would go back and begin to double them up. Then we would go on to the 3p and fill that one, and then we would put 1 in each of the 3p, and now we're going to put our last sulfur electron and double it up back up here in the first 3p orbital. 2, 4, 6, 8, 10, 12, 14, 15, 16. Sulfur has 16 electrons that we have to represent in our orbital diagram. So what is the code? Here's our code. 1s2, 2s2, 2p6, 3s2, and 3p4. Let's do silicon. Silicon, we fill 1s first, then 2s, then we put 1 in each of the 2p. We still have more electrons, so we go back and double them up. Then we have 3s is full, and now we begin to fill the 3p. We only have 2 more electrons to worry about, and we're going to spread them out across the first 2 3p orbitals, both pointing up or both pointing down, doesn't matter. We've got 2, 4, 6, 8, 10, 12, 13, 14. We have our 14 electrons represented. The code would be 1s2, 2s2, 2p6, 3s2, and 3p2. Neon. 1s gets filled. Then our 2s gets filled. And neon has how many electrons? Well, it's got 2, 4, 6, 8, 10. It's got 10. So we're going to go, now they're all going to get full, but I'm just going to put them one at a time here, just to follow the rule. Then we would go back and double up. Now we've got all 10 electrons in our orbitals, and we have a 1s2, 2s2, and a 2p6. Okay? Extension questions. Here's another model, Model 3, the orbital diagram for an atom of element X. We're not being told what the element is. There is no element X. They're saying it's an unknown element. But if we're given this information, we should be able to identify that element and tell a little bit about it. Consider the orbital diagram in Model 3. How many electrons are there in one atom of element X? 2, 4, 5, 6, 7, 8, 9, 10. There are 10. 10 electrons. Identify element X and provide its ground state electron configuration. Assume the atom is neutral. So if it's neutral, that means the same number of electrons and the same number of protons. I mean, the electrons and protons are the same, the number. So it must have, if it has 10 electrons, it also is going to have 10 protons. So its atomic number is 10. What element is that? Well, hey, we just dealt with one that had 10 up here, right? Wasn't that neon? Must be neon. Okay? And E for neon. And C, is the arrangement of electrons in the orbital diagram in Model 3 higher in total potential energy or lower in total potential energy than the ground state electron configuration of element X? Explain your reasoning. So what we see here is, if we have 10 electrons, we would have expected that this position right here be full, but it's not. Why? Well, this element somehow must have gained some energy, maybe from electricity or maybe from heat or something like that. And this electron, boop, jumped up to a higher energy level because it gained energy. So this is an example of an excited state. It's not ground state. So we know because an electron is at a higher energy position. Therefore, it is an excited atom. It is at an excited state. Okay? Or, and the way they state it is at a higher potential energy. It has more potential energy. And it is storing that potential energy in the fact that the electron is further from the nucleus. Once that electron drops back down, it's going to release that energy. An excited state electron configuration is any electron configuration for an atom that contains the correct number, total number of electrons, but has a higher total electron potential energy than the ground state electron configuration. By the way, you will know that when you draw this diagram, you will see a gap. You'll see an electron that jumped up. You would also see that because if I was to write this configuration, 1s2, 2s2, 2p5, and then a 3s1, you should notice, hey, usually that fills up with 6. What's going on here? If this is 5 and this is 1, that means that electron moved up and there's a gap there. So you can see it either way in the diagram or the configuration. You would notice, hey, that's not a ground state situation. Write an electron configuration for an element that shows the electron in a different excited state than the one illustrated. So we could have a 1s2, 2s2, 2p4 if you want, and then a 3s1 and a 3p1. Somehow now 2 electrons got moved up to higher energy positions. So there's lots of different variations there. That's just one more possible configuration for an atom at a higher energy, potential energy position. 18. We have all these different possible configurations. Each orbital diagram shown below describes an excited state of an atom of a different element. Use the orbital diagrams to complete the table. So this is element A, this is element B, this is element C. They're different elements. And they're telling us that these are excited states. Okay? Should be obvious because you can see that the lower orbitals are not being full before we have electrons in the higher orbitals. Okay? Here this one's not full, you have an electron here. Here this is empty, completely empty, as is this one. These are starting to be filled up here. Okay? So let's write down the correct excited state electron configuration for A. Just tell me where the arrows are. That's all you have to do. And how many in each of the orbitals. 1s2, 2s1, 2p3, 3s1, and that's it. For B, it is 1s2, 2s2. Yes, we have the 2p full, 2p6, but the 3s only has 1, as does now the 3p. For C, you've got 1s2, 2s2, 2p3. Usually it's 6 if it's full, so these other electrons got moved up. There's no 3s. 3s is void, so I'm not even going to put it. And then you've got 3p6. Alright, identify the element. Again, we're going to assume that these are neutral elements. Excited, by the way, excited configuration doesn't mean that it lost or gained electrons. It just means the electrons got excited and moved up to higher energy levels. Identify the element. We're going to assume that these are all neutral. So all we do is we count the number of electrons, assume that's the same as the number of protons, which is its atomic number, and we have the identity. So this one has 2, 3, 4, 5, 6, 7. 7 is nitrogen. This one's got 2, 4, 10, and 12. 12 is magnesium. This one's got 2, 4, and 7, and 6. That one is going to be aluminum. Ground state electron configuration. Alright, if all of these electrons were to lose energy and go back to their ground state, then let's write these accordingly. You would have 1s2, 2s2 would be full. Again, how many are we doing here? We got 2, 3, 6, 7. We're doing 7 electrons. So there's 4. Then we do 2p. 2p. We need 3 more. Okay? That's it. Here, 2, 10, we had 12 electrons. So 1s2, 2s2, 2p6, there's 10, and then the 3s2. Over here, we had 6, 9, 10, 11, 12, 13 electrons, is that right? Okay. 13 electrons, so we would have a 1s2, 2s2, 2p6, that gives me 10, and then the 3s2, and then the 3p1. Complete the table for each of the excited state electron configurations given. So now they're telling us here, this is an excited state. We're going to say the element, we're going to put the ground state, and the orbital diagram for ground state. So we know this is excited because this 2s didn't get full or filled before the 2p did. All we do to name the element is count the number of electrons, and that's going to be the same as the number of protons, and that's your atomic number. So we've got 2, 3, 4, 5 electrons, that is boron. And 5 protons also, okay? Let's come down here, 2, 4, 6, 8, and 9. 9 is fluorine, we've got 9 electrons, atomic number 9. Ground state would then be, let's drop everything down to the lowest energy position, 1s2, 2s2, 2p1. There are your 5 electrons. Here, 1s2, 2s2, 2p6. Notice that's not the case here. Some of them moved up. And we need to have 9. Oops, I went too far already. It should be a 5 right here. Okay, sorry about that. That should be a 5 because I should only have 9 electrons. Okay? And then the orbital diagram, well, you could have an orbital diagram here. I'm just going to put lines, okay, if that's all right. I'm just going to put lines. So we'd have up and down, and then one up. Or it could be down, doesn't matter. You can have up and down, and you're going to have one in each of them first, then go back and pair them up, so we have all 9 represented. Okay? Alright, there you go. You know about electron configurations now. You know about energy positions, energy levels, and you know about excited state, ground state, and we're going to carry this over into the next video, the next topic, when we talk about the periodic table, because you're going to see a connection between the electron configurations and the positions of those elements on the periodic table. And we'll see you then.